Let us solve another problem related to the design of induction motor, only the stator design. Okay, so let us read out the problem as well as note down the given parameters. Determine the approximate diameter and length of stator core. So we have to find out the diameter and length of stator core. Number of stator slots, SS, we have to find. The number of stator conductors, total number of stator conductors, that is 6 into number of turns per phase. For a 11 kilowatt 400 volt 3 phase 400 volt, output power is 11 kilowatt, P out is equal to 11 kilowatt, voltage is 400 volt. Number of poles, P is given as 4. The speed is given as 1425 rpm. So in case of induction machines, the speed given in the question will be the rotor speed. So here 1425 rpm is the rotor speed, but we need the synchronous speed in the output equation. So this is always the rotor speed. We know that in a synchronous machine, the rotor always runs at a speed which is slightly less than the synchronous speed. So the synchronous speed will be the nearest value to 1425 rpm. So the nearest possible synchronous speed is 1500 rpm. In this case, the nearest possible synchronous speed is 1500 rpm. So we got the synchronous speed. So delta connected induction motor. So stator is delta connected. Then B average is given. B average is equal to 0.45 Weber per meter square. AC is equal to 23,000 ampere per meter. Ampere conductors per meter. Then full load efficiency. Efficiency is given 0.85. Power factor is given as 0.88. And here, instead of giving the design feature, the L by tau ratio is directly given. So L by tau is 1. So it need not be always the case. In most of the cases, only the design feature, desired design feature will be given. It will be cheap price, good power factor, best power factor, etc. So the corresponding L by tau ratio should be known to you. Okay, you have to by heart the L by tau ratios corresponding to all the design features. So here they have given it directly. L by tau is equal to 1. And given that the stator winding is a double layer winding. Double layer winding is used in the stator. So this much of data we know. So with this we have to design the particular machine. So let us move on to the solution. So as we have already discussed, the first step in designing an induction motor should be the conversion of output kilowatt to input kVA. So we can calculate the input kVA Q as output kilowatt divided by efficiency into power factor, which is equal to output kilowatt rating is given as 11 divided by efficiency is 0.85 into power factor is 0.88. So we will get the kVA rating as 14.7 kVA, input kVA rating. So now we have to calculate main dimensions D and L. So main dimensions are always calculated from the output equation. So here the equation is input kVA. For induction machines, induction motors, output equation corresponds to input kVA. Input kVA Q is equal to C0 D square L into NS. 14.7 is equal to C0. C0 is 11 into B average into AC into KW into 10 raised to minus 3 into D square L into ns. ns is the synchronous speed in rps. So we know synchronous speed in rpm 1500 and synchronous speed in rps is obtained as synchronous speed in rpm divided by 60, that is 1500 divided by 60, and it will be equal to 25 rps. Okay, now so from this equation we will get the value of d square L. So d square L will be equal to 14.7 divided by 11 into B average. B average is 0.45 into AC is 23,000 into kW. It is not given, we can take it as 0.955 into 10 raised to minus 3 into ns, that is 25. On solving this, so here we will get the value of d square L as 0.0054 meter cube. 0.0054 meter cube. On solving this equation, you will get this value. So we have d square L. Now we have to separate d and L from this product d square L, and we always perform this separation using the L by tau ratio or by using the peripheral speed. So here in this problem, L by tau ratio is given as 1. So that means L is equal to tau. Tau is pi d by p. So we have L is equal to pi into d divided by p. P is the number of poles and it is 4. Okay. So L is equal to pi d by 4. Now we can substitute this relationship in L is equal to pi d by 4 in this equation d square L. So we can write equation number 1 as d square into L. That is d square into L is pi d by 4 is equal to 0.0054 meter cube. That is pi by 4 into d cube is equal to 0.0054. So solve this equation and find out the value of d. So you will get the value of d as 0.1902 meter, or a value near to this. It is not the approximate exact value. It is not the exact value. You will get a value near to this. It can be 0.189 something or like. Okay. So this is the value of d. Now substitute this value of d in this equation. Substitute d in equation number 2. Then pi into d divided by 4, you will get the value of L. So the value of L that you are going to obtain is L is equal to pi d by p. So pi d by p, that is pi into d is 0.1902 divided by 4, and value of L will be 0.1494. So for instance, let us approximate it as 0.15 meter. Okay. So we have got the main dimensions d and L. So what is this next step? So all the problems are having the same sequence of solution. First of all, calculate the main dimension, then go for calculating the turns per phase. So you have to set a common pattern for solving the problems. So first of all, calculate d and L from the output equation using the L by tau ratio. Thereafter, go for calculating the turns per phase. So we will calculate turns per phase from the equation of induced EMF. So we will get the equation for turns per phase as the induced EMF per phase of the stator divided by 4.44 F into 5 into kW. Okay. Now, so induced EMF of the stator. This is turns per phase. So this should be the induced EMF per phase. Okay. Here in this question, it is given that the stator is delta connected. So given line voltage can be used as the phase voltage also. For delta connection, line voltage is equal to phase voltage. So we know the value of frequency. We can take kW as 0.955, but phi is unknown. So now how can you calculate phi? So we will always calculate phi from the value of B average. So B average is equal to P phi divided by pi dl, implies phi is equal to. Now phi can be calculated as B average into pi dl divided by P. So B average is 0.45 into pi into D, we have got it as 0.19 into L is 0.15 divided by P. Number of poles is 4, and on solving this we will get the value of phi as 0.01 Weber. Now substitute all the values in the equation for turns per phase. The induced EMF per phase is 400 volt. It is given in the question. The supply voltage is 400. Then divided by 4.44 into frequency is 50 Hz into flux is 0.01 into kW is 0.955. So on solving, we will get the value of turns per phase as 188. So using this, we can calculate the total number of stator conductors also. Okay. So we know that total number of conductors is equal to 6 into Ts, which is equal to 6 into 188. Okay. So now the next step, after calculating the turns per phase, the next step is the calculation of number of stator slots. Okay. So we will calculate this number of stator slots by assuming different values for Q, that is slots per pole per phase. Q is the slots per pole per phase. So its minimum value is 2. So we'll assume Q is equal to 2, Q is equal to 3, Q is equal to 4, etc. and correspondingly calculate the total number of slots. Then check whether the corresponding slot pitch is within the limits. Okay. So this procedure can be used for all the induction motors. While calculating the number of stator slots, choose different values for Q starting from 2, 3, 4, etc. Then calculate corresponding total number of slots. Then for each case calculate the slot pitch. If the slot pitch is within the limits, we can choose that corresponding value. So with the Q is equal to 2, we can calculate the total number of slots as, so Q is slots per pole per phase. So total number of slots is equal to Q into number of phases into number of pole. So 24. Then corresponding to 3, total number of slots is 3 into number of phases into number of poles. 36. Corresponding to 4, 4 into number of phases into number of poles. It will be 48. Now corresponding to each of these case, calculate the value of slot pitch. So with the Q is equal to 2, slot pitch becomes YSS is equal to pi D by SS, which is equal to pi into D is 0.19 divided by 24. It will be some value 24.87 mm. Then with the Q is equal to 3, we will get YSS is equal to pi D by SS is equal to pi into 0.19 divided by 36 is equal to 16.58 mm. And if we choose Q is equal to 4, it will be a value which is less than 15 mm. So here this machine is a large machine, 11 kilowatt machine, and YSS should be in the range 15 to 25 mm. So if we choose Q as 4, it will be less than 15 mm. So we cannot use this. But these two cases are possible. Okay, these are between 15 and 25 mm. So what we have to do? So the best choice, the best way that we can design this machine is to choose as much number of slots as possible. Choose as much number of slots as possible. Okay. So better to choose Q is equal to 3. It is an advantage to have a larger number of slots because it will, with larger number of slots, tooth pulsation will be less, overload capacity will be more. So there are advantages. So we can choose Q is equal to 3. So, and always keep in mind that if Q is equal to 2 and Q is equal to 3 are possible, better to choose Q is equal to 3. In most of the problems, Q is taken as 3. Okay, if you go through different problems, you can see that most of the cases, the value of Q is taken as 3. So here the better choice is Q is equal to 3, and hence the total number of slots will be equal to 36. Okay. So total number of stator slots. Equal to 36. So next step, we have to calculate conductors per slot, which is equal to total number of conductors divided by total number of slots. So total number of conductors is 6 into 188. 6 into 188. 6 into 188 divided by 36. So it will become 31.333. Okay. So in case of conductors per slot, that means how many conductors are to be placed in a single slot. It should be an integer. We cannot place fractional number of conductors in a particular slot. So this should be an integer. And how will you approximate this value to the nearest integer? If you are going for the nearest integer, it should be 31. But in the question it is given that we have to use a double layer winding. So what is a double layer winding? In a double layer winding, in a particular slot, there are 2 coil sides. There are 2 coil sides per slot. Okay. So that is a double layer winding. So total conductors in a particular slot will be 2 into number of coil sides, number of conductors per coil side. Okay, so we have to use a double layer winding. What is a double layer winding? In a double layer winding, there are 2 coil sides in each slot. So, ഇവിടെ ഒരു coil side ഉണ്ട്, ഇവിടെ ഒരു coil side ഉണ്ട്. And in a particular coil side, there are a number of conductors. So here also there are a number of conductors. So total number of conductors in this slot will be 2 into number of conductors in a single coil side. That means it will always be a multiple of 2. In case of double layer winding, conductors per slot will always be a multiple of 2, or conductors per slot will be an even integer. So for double layer winding, this is an important point. For double layer winding, conductors per slot will be an even number. So instead of approximating it to 31, approximate it as 32. So we will get conductors per slot is equal to 32. So we have got conductors per slot as 31.33 with our calculated value of total number of conductors. But we have chosen some other value, that is 32. So with this value 32, we have to recalculate the total number of conductors. So total conductors becomes 32 into 36, which is equal to 1152, and new value of turns per phase, actual value of turns per phase becomes total conductors divided by 6, that is 1152 divided by 6, that is equal to 192. So initially we have got it as 188, but in order to make a double layer winding, we have to use 192 turns per phase. This is how this machine can be designed.